Yeah, last week we did an introduction to trigonometry. We understand what the functions are now, sine, cosine, tangent. Today we're going to do inverses and identities. Both start with I. That was kind of intentional. So that's what we're doing today. More trigonometry. So inverse trig, look at these three things. And then trig identities, and do a lot of practice. Okay, so CSC, SEC, and COT. Cusk, sec, and cot. So those are not as easy to say as sin, cos, and tan, but I'm going to show you what those are. So first, inverse trig. So what does inverse trig mean? Well, let's say we take a function f of x equals y. If we take the inverse function of it, this is how we usually write it, we can plug in y to get x, right? That's the definition of an inverse function. If the first function, if we plugged in x, the output was y, the inverse function takes in the output that we just had, and the output of that would be the input that we had. So like it kind of swaps them. Okay. So the initial function we could plug in x and y comes out as the output. The inverse function, if we put in y as the input, x comes out as the output. So for sine, cosine, and tangent, they're all functions, right? So we have like sine of x here. This is technically a function equals y, let's say. The inverse function, just we're doing the same notation here. We put the -1 right there. Sine, inverse sine. So this is not saying like we're taking it to the -1 power. That's something else. So this means we're taking the inverse, which means if we plug in y here, we're supposed to get x. So in the case of this, we can only plug in angles for x, right? By the definition, we plug in angles into a sine function, and out comes the ratio. Ratio adjacent opposite over hypotenuse. So the angle goes in as the input. The output is the ratio of the opposite of the hypotenuse, whatever that would be, like whatever the actual value of sine of x was. Right? If we take the inverse now, well, the input is actually the ratio, and the output generates the angle. So we plug in the ratio, and it tells us what angle created that ratio. So as an example here, what is the sine, inverse sine of 1? So we plug in this ratio here. This is the value that we output after we applied the sine to some angle, right? So we got to find what angle that was. Well, what angle would give you a sine of 1? Pi over 2, right? So pi over 2 is the inverse sine of 1. Okay, so we're plugging in a ratio here, and the output is the angle that made that ratio. But if we notice here, there are multiple answers. Because technically, if we have 2 pi plus pi over 2, that also works. Right? Because if we have 2 pi plus pi over 2, we're going around in a circle, back at where we started, and then we just add another pi over 2. And the sine is still 1. So there are multiple answers to this. There are multiple values of this thing. Okay? So be sure to watch out for that. There are multiple possible values that this inverse sine can have. All right? We could also have 4 pi plus pi over 2. As long as we got like a full revolution, and then we just add a little bit, that's pi over 2, we're going to get back to this point, which means it's always going to correspond to this. Any questions? So this is what inverse trig is. So we put a -1 in there. And this tells us it's the inverse of the function. This is not equal to 1 over sine of x. No. Okay. So to write the -1 there, it doesn't mean we're raising it to the -1 power. It means it's actually a different function. It's an inverse function. Takes in the ratio, outputs the angle that made the ratio. Okay, so because we have multiple answers, we often have to set a limitation. So this basically tells us we can only choose angles that are from 0 to 2 pi. Because technically there's an infinite number of angles that are possible that could correspond to this value, whatever, right? So we set a limit there. So only consider the possible angles within this range, 0 to 2 pi. Should take 3 minutes. Okay, so the first one, the ratio is here. That's the value, right, of the whatever it was, right? So what angle would correspond to a sine of root 3 over 2? Well, since the sine is the y-coordinate, kind of looks like this, right? A unit circle. Looks like this point works because the y-coordinate is that, but this point also works. So we actually have two solutions within this range. So what are these two angles? Well, this is pi over 3. This is 2 pi over 3. So this thing can equal to pi over 3 or 2 pi over 3. Next one is very similar. What values of cosine would give us negative root 3 over 2? Cosine is in the x-coordinate, so that's kind of like there. And it looks like Those are our two solutions. So this one is 5 pi over 6. This one is 7 pi over 6. So our two answers are 5 pi over 6 and 7 pi over 6. Next one, the tangent is 1 over root 3. So if you don't know what angle that corresponds to, so since this is such a nice answer, we can just experiment. Like which one of the landmark angles would apply to this? Right, so we got some landmark angles like pi over 6. These are the ones that we actually have definite values for the sine and cosine because we apply these special right triangles, right? So since this is a pretty precise number, we can assume that it's one of these special triangles. So let's first try pi over 6. The tangent is the y over the x because it's sine over cosine. So the sine is 1/2, the cosine is root 3 over 2. So the y over x is actually 1 over root 3. So yes, pi over 6 is one of our solutions. Are there more though? Tangent is y over x. So if you think about it, that's actually the slope of this line. That's the slope. So that means this is another solution because this line has the same slope, which means 7 pi over 6 is also an answer. So pi over 6, 7 pi over 6. Last one. This one should be relatively simple. -1 right here, which means 3 pi over 2. We don't have more because like it's on the y-axis, right? If we had something like this, we could there were two solutions because it would like just reflect across the y-axis. But in this case, we only have one solution. So 3 pi over 2. Any questions? So if it looks like I'm going a little fast, it might be because you have to do some more practice. So there are lots of good websites out there. Just search for unit circle practice, and then you'll find it. Okay. Also, if you haven't done the homework, that's like the first thing you should do. So, but if you're looking for extra practice and you've already done the homework, there are lots of websites out there. So just search unit circle practice, and you should find it. Okay, they're all like online games. Okay, now we're going to go to these three things: CSC, SEC, and COT. Remember what I said? We can't have sine of -1x. This is the inverse, right? So you might be wondering, then how would I ever write sine of x to the -1 power? How do I do that? What if I wanted to do this, right? So if I haven't said this before, well, when we apply powers to trigonometric functions, we often write the power right here. So if I want sine x squared, it's the same thing as sine, and I put the 2 right here. It's just a different way we write it. This still means 2 sine x's multiplied by each other, but we just write the 2 here for, because that's just how we do it. That's how the math people decided. So yeah, so the 2 goes there, all right? So when we're doing powers of trigonometric functions, power goes in between the word and the variable. So you might be wondering, how do I do this? How do I write, since we normally put the power between the variables, if I want to write sine of x to the -1 power, I can only write it this way. But this is already taken up. The definition of this is inverse, not the 1 over sine of -1. So how do we do it? That's where these things come in. CSC is what we write instead of sine x to -1. This is equal to CSCx. This is cosecant. SEC is our way of writing 1 over cosine, right? Because we same as sine, we can't write this because this would correspond to the inverse cosine, not 1 over cosine x. So if you want to write 1 over cosine x, we just write sec x, secant. Cot is cotangent. and that's 1 over tangent. Okay, just new ways we can write things. There's nothing really special about these except they're just 1 over the functions that we already know. So there should not be too much new here. Any questions? So one good way to memorize these is that it's kind of like swapped. Right? Remember we had like S stands for sine, right? CSC, it starts with the C. So instead of S with S, it's S with C now, and then C with S. Okay, it's kind of like swapped. We don't have, like the sine is not the secant, these don't correspond. The sine corresponds to the cosecant, the cosine corresponds to the secant. It's kind of like C and S, they're like, I don't know how to say this, but like that's one way to memorize it. There's a C and an S there. Right. I've got these trig identities, right? So we've got our Pythagorean identities. If you did the homework, this would be very familiar. First of all, let's look at the easy one. The easy one is negative angle identities. These are not really identities. So identities are basically like formulas we can use for trig. So these two tell us that the cosine of negative x is still cosine x, which is basically self-explanatory because if we have x here, cosine negative x is right here, and they still have the same x coordinate. Right? And the cosine is the x coordinate. So cosine of negative x is the same thing as cosine x. Right? They're the same value. Because if we took it as negative x here, we have the same x coordinate. But for sine, we have the negative of the y coordinate. Right? For the first one, we had this positive, and then when we took the negative angle, we made it negative. So the sine of negative x is the negative of the sine of x. Okay, those are pretty self-explanatory. You don't really need to memorize them. So now for cofunction identities. We looked at these in the homework. So if you did the homework, you know why these are true. If you didn't do the homework, just accept these are true. Okay, so these functions can go, these identities can go the other way around too. Like I could write cosine here and sine here, and it would be it would still be valid. Okay, so Pythagorean identities in the homework we proved that this is true. The other two are just different forms of this formula. All right. So to get to these other forms, I'll just demo with the first one. How do I get to this form? Start with our original Pythagorean identity. Divide everything by cosine squared x. This cancels out. Sine squared x over cosine squared x, that's tangent squared x. Because tangent is sine over cosine, right? So the next term is just a 1. And the last one is 1 over cosine squared, which we would write as secant squared. And that's just the other form that we could have. So these are just, the other two are just different forms of this Pythagorean identity. So you really only need to memorize the first one. And they've got a double angle identities. These are the most complicated ones, but these are some of the most important ones. So sine of 2x is 2 sine x cosine x. And then for cosine 2x, we have these 3 forms. If you did the homework, this should be very, very, you should already know these, right? So, and you know the proof for them. So good job if you did the homework. If you didn't, I don't know, like memorize these or something. Okay. So identities, any questions here? That's again why it's important to do homework, because you might miss out on a little bit if you don't do it. So let's apply these identities. So we have these problems. It's just practicing our identities. So verify that this equation is true. So you want to make sure, so you only alter one side of the equation. I can only allow you to change one side of it so you can match it to the other side. Okay. So this is the problem here. So you can either choose this side to change around, and somehow with your identities, you got to get it to match this. Okay. Or you could have chosen this side and do something with your identities to get it to match this side. So it's up to you to choose which one you want to alter, but you can only alter one side. Okay? Give you 3 minutes. So if you're not quite sure how to do this, maybe I can demo this one for you. So we're going to choose one side of this equation so we can match the other side. Well, which one do we choose though? Right, so that's the question. Well, what we generally want to do is we know how to simplify things, right? But it's harder to make things more complicated. We're just hardwired to make things simpler, right? So we have to choose the more complicated side to get it to look more like the simpler side. So the more complicated side looks kind of like this one. It's got two terms multiplying by each other. So I'm going to alter this one only to get it to this using my identities. So the first thing I'm going to do is I like to think in terms of sine and cosine. So tangent negative x is sine of negative x, cosine negative x. This is multiplied by the cosecant of negative x, which is 1 over the sine of x. Okay, so now we can apply our negative angle identities. Sine of negative x is negative sine x. Cosine negative x doesn't change, so it's just cosine x. Cancel these now, so it's just negative 1 over cosine x. This side has a cosecant. Cosine is secant though. So 1 over cosine x, this is negative secant x. You can also write this as, so negative secant x now. How do we get the cosecant? Well, we're going to use our cofunction identities. So negative secant x is negative cosecant times pi over 2 minus x. Right? Now let's apply our negative angle identity. Right? So cosecant is 1 over sine, right? So we know that the negative angle identities that apply to sine are going to also apply to cosecant. So if we take the negative out here, so remember, negative sine of x is sine of negative x, right? So the negative can actually go inside. So now we just have cosecant of negative pi over 2 minus x, which is cosecant of x minus pi over 2. And that matches. So that's the general process we're going to go through. Any questions here? If not, let's go on. Got this one now. I think it's pretty obvious which one you should be changing here. Okay. Alter the left side. First of all, I see pi over 2 minus x. It tells me I have to do my cofunction identity. So the secant squared will turn into cosecant squared of of just normal x minus 1. Cosecant squared turns into a secant squared. Okay. Looks like we have squares in here, which reminds me of the Pythagorean identities. And it does. Tan squared x plus 1 equals secant squared. And cotangent squared 1 equals cosecant squared. Okay, so cosecant squared, if you move this 1 onto both sides, it's obvious that this is tan squared and this is cotangent squared. So tan squared x times cotangent squared x. And by definition, cotangent is 1 over tangent. So this is the same thing as doing 1 over tangent squared times tangent squared. Obviously cancels out to just get 1 matched. Any questions? Let's go to the next one. Okay, so it's common procedure to put everything in sine and cosine. And I'm going to be simplifying the left side because that looks more complex. So remember, cotangent is 1 over tangent, which means it's the reciprocal of sine x over cosine. So it's cosine over sine. Looks like I can factor out a sine x from this. So I'll factor that out. I have 1 minus cosine x, 1 plus cosine x. If we actually multiply these, let's see what happens. It's a difference of squares, so 1 minus cosine squared x divided by sine x. Ooh, I see a squared in there, so it's Pythagorean identity. So we're going to use the identity sine squared plus cosine squared equals 1. Right? So 1 minus cosine squared is sine squared. So sine squared x over sine x. 1 cancels out, so just sine x. So we've got it. This matches. If you're confused about any of these, I highly, highly recommend that you do the homework from last week, because that shows you why all these are true, and it gives you more practice on just memorizing them in general. Okay. Okay, so this one's relatively simple. I'm going to alter the right side because it has a fraction. It's a little more complex. So the trick here is to notice that we got to get a cosecant minus a cotangent in the numerator in the end, right? So it makes sense that we could multiply the top and bottom by that value. And hopefully the denominator will cancel out, so we just get a 1. So we're only altering one side of the equation. So now we've got cosecant minus cotangent over, well, this is the difference of squares. Cosecant squared minus cotangent squared. Pythagorean identity shows that this is just 1, so it goes away. And we can see that this does match that. Okay. So another strategy you could use is just to multiply top and bottom by something. And Yeah, so a lot of strategies, this is basically going back to your algebra. What kind of strategies could you use to alter equations? And there are a lot. Okay, so this section of trigonometry is more like algebra than geometry. Next week we'll go more into geometry again. So yeah, that's generally what's going on here. Let's go on. Another one. This one looks pretty complex, but don't be scared, okay? Okay, so let's take a look. I'm going to simplify the left side because it looks pretty complicated. So going back to our algebra skills, look like we got two quadratics here. Guess what? I wonder what that tells us. Well, it happens to be that these two quadratics, I can factor them. So if I factor them, hopefully something will cancel out, right? I don't know if something will, but I will attempt the strategy anyway. So for the top, we can factor this as a difference of squares. Bottom, we can factor this as normal factoring. Minus 3 cotangent x plus 1. Ooh, very nice. We have canceled out these. So all we have left is cotangent x plus 3 over cotangent x plus 1. This side has cosines and sines, which means it should be, the strategy next should be to replace these with cosines and sines. So cosine x over sine x, cosine x over sine x. Let's multiply both sides by sine x so we don't have a fraction in a fraction. I just have cosine x plus 3 sine x over cosine x plus sine x. And that is matching, which is very nice. Okay, that's all the time I have left for today. So if this was a little, if you don't think you had enough practice today, there's a lot of practice in the homework. So that's always there for you to use. I'm not going to require you to submit it, but if you truly want to take advantage of this class and to learn, then do it. Okay? And if you didn't do last week's, do that one too. So I'll see you guys next week. Bye.